last lecture by Olga Mena and the last lecture overall. Please.
Okay, great. Thank you. Here in the first few days, I know that many of you are interested in fundamental fields, so I slightly changed my last lecture to try to use black holes as particle detectors. The idea, we discussed it already, it has to do with energy extraction. So we saw how we could extract energy away from black holes if we use particles, okay? The idea was simple, you lower stuff into the ergo region and you let the black hole do the rest, just frame drag everything. But there's a wave analog of this stuff. I need hair for this. There's a wave analog of this that I'd like to talk to you about. Actually, I had an interesting discussion, I think last night about this, okay? This is called rotational superradiance, and it was, I think, devised by, by Zeldovich in our field, but slightly before by other people. There's different versions of this mechanism. Let me give you one of them, which I think works very well for everything related to rotation, okay? The idea is to try to extract energy or transfer energy within a system where one component is spinning. The Earth-Moon system, actually, is a very nice example of this, okay? You have the Earth here, it's spinning, it takes 1 day to give a full rotation around its axis. And then there's the moon. The moon goes around the Earth once every 28 days, roughly, okay? But now look at, an approximation of how the Earth looks like. It's spinning under the oceans. It's a very simplified approximation, okay? So bear with me. By the way, this picture was by Darwin, the son of the Darwin, okay? And the idea is the following. Because the Earth is spinning so fast, so you see, the moon is rising tides on the Earth here, okay? But because the Earth is spinning very fast, and because there's some friction between the crust and the ocean, the tidal axis is slightly misaligned with the Earth-Moon axis. You see, there's a tidal angle. It's very, very small. I had to make it large, otherwise you wouldn't see it, okay? Phi is really a small number, but I've just zoomed out that stuff, okay? But now, so what does it mean? Well, it means that there's friction. So as time goes by, the Earth should be slowing down, right? I mean, this is kind of intuitive. But this is a problem, in some sense, because the system is isolated. The heck, where is angular momentum going? So angular momentum is actually going to the moon. So the moon, to conserve angular momentum in the system, is getting farther away from us. It's taking the energy out of the spinning Earth, okay, and placing it in energy, kinetic energy of the moon. So the moon is, by the way, this was measured. This has been measured for many years. It's the pace at which the moon is getting farther away from us is roughly the pace at which my fingernails grow, okay? 3 centimeters per year. They are not special, huh? So what's the final state of this process? Well, what's driving this is the friction between the Earth and the oceans. But what's driving that is the misalignment. I hate this device. Is the misalignment between the Earth-Moon axis and the tidal axis. If they were the same, there would be nothing. So the final state of this is an Earth co-rotating with the moon. The day will be the month. Okay? And now you can suspect that this process actually occurred with the moon millions of years ago. That's why the moon is always facing with the same face towards us. Okay? This is called tidal acceleration in planetary physics, but exactly the same thing happens with waves. So what happens is You throw a low frequency wave at a spinning object, any spinning object, okay? So if I do this, and you throw a sound wave to this guy, you're going to extract energy away from this guy. This has been measured, by the way, 3 years ago. Okay? So if you throw a wave, an electromagnetic wave, or a gravitational wave at a spinning black hole, it's going to extract energy away from that spinning black hole. It's unbelievable. It seems unreal. Okay? But you can actually calculate it. It's all in the notebooks I sent. Okay? So you throw a field with frequency, so it's a monochromatic field, frequency omega. Okay? You decompose it in with this, well, the standard thing we've been doing for the last 3 lectures. Okay? We decompose the field in spherical harmonics, in this case probably something slightly different because the geometry is spinning. We call it spheroidal harmonics. There's an azimuthal time dependence that we used. It's the standard one, okay? It's characterized by an integer m. And you will find the following. If you throw this wave at the spinning black hole, then the reflection coefficient, we saw it yesterday, we calculate this, okay? The reflection coefficient is larger than 1. You get back more than you threw in if and only if the frequency of your field, omega, small omega, is smaller than the angular frequency of your black hole. This is the analog of the moon going very slowly around the Earth. Okay? So this condition, omega, the frequency of your field, smaller than this guy, is really the moon, the Earth-moon thing. Okay? M tells you that your wave you sent in cannot be axially symmetric. So if M is 0, means no azimuthal dependence, you get nothing interesting. Okay? And the same for the Earth and Moon. If you made the Moon a ring around the Earth, there would be nothing, right? Because the tides would be symmetric. There would be nothing to tidally accelerate the Earth. Okay? So the Moon would not get farther away from us. There would be, well, boring physics. Well, exciting physics, we would always see the Moon everywhere in the sky, but... Okay. So you can calculate this. You can calculate the amplification coefficients when you throw a wave onto a spinning black hole. They're here. So Z, for me, my definition is the energy that comes out when I throw in something with amplitude in. -1. This gives me really the gain that I get. Okay? As a function of frequency. And I do that for scalar fields. So solid black lines are numerical results that you can calculate with a notebook. Dashed lines are just some small frequency approximation that where we can solve the equations exactly. It's not a very impressive effect. It doesn't look like it. I mean, for a scalar field, the maximum amplification factor, it's here. It's of order 0.4%, and the black hole needs to be really spinning fast. Okay? For an electromagnetic field, so waves, light, you throw light at the spinning black hole, and if the black hole is spinning very fast, you might get 4% amplification factor, and that's not so bad. Okay? And if you throw a gravitational wave at a black hole with the right frequency, then you get a huge amplification factor, 140%. Okay? So almost twice of what you sent in. You send a joule and you get back 1.4 joules. Not bad. Okay? Now, when doing this, he actually didn't calculate this. Zeldovich didn't calculate these numbers, but he understood that he could do something more with this system. Okay? And the something more is a black hole bomb. I mean, if you know how to extract energy from a system, you know how to make it unstable, right? And the idea was the following. You throw a low frequency wave at this guy, and you prevent the wave from escaping, right? You have a spinning black hole, you throw this low frequency wave, the low frequency wave gets amplified, and then you place a mirror far away, and you force that guy to go back, right? So there you go, an exponential cascade of energy extraction, always going back and forth between the mirror and the ergo region, extracting energy and growing exponentially. Of course, at some point, by the way, I think we celebrate the 50 years of the Presen-Tarkovsky paper on black hole bombs. It's a Nature paper that at some point claims if there's an alien civilization that actually wants to use this to build, to have a power machine instead of using wind or nuclear energy, then at some point, of course, the mirror is going to break because the pressure of radiation is really just very large. Okay? Now, the twist is the following. If I have a pen, I do. So we looked at the Klein-Gordon equation for a generic massive field, okay? And it looked something like this. d2 dr star 2 minus d2 dt2, the usual wave-like stuff, okay? And then the potential. But V, the potential when you have a mass term, looks like this. 1 minus 2m over r, and then L plus 1 over r squared, plus the mass of your field. Okay? The mass of the field is important. Why? Think about a monochromatic pulse. This guy is just omega squared times the field. Okay? Look far away. What happens asymptotically? Well, then you get d2 dr star 2 plus this guy is 1, this guy is 0, this guy is omega squared, so you get plus omega squared minus mu squared, psi is 0. Okay? You remember when we wrote down the asymptotic behavior of the field. If this guy is 0, it's really just an outgoing wave. But if this guy is non-zero, now the solutions change totally. The solutions are e to the plus or minus square root of omega squared minus mu squared r star, right? Far away. So you see what you did. You actually have a mirror. If you have a sufficiently low frequency field, if omega is very small, okay, this guy is going to be a complex number. Actually, there's an I missing here. Okay? So one solution grows exponentially, the other gets stuck to the space-time. If you want regularity, you want to rule out the exponentially growing solution, you have a mirror. Right? So you actually, nature might be giving you mirrors out there. So maybe there are black hole bombs out there. Okay? Good? Why did this? I think my PowerPoint is crazy. Oh. And now? Well, I can do it like this. Wait. I think I'll kill all of this. Right? Very good. So, is this actually interesting? And we need to know timescales. For this to be interesting, we need to know timescales. So here's the system we're solving. Okay? You take the simplest thing you can, either a very simple minimally coupled massive field, the stuff we saw. You need to have some mass. You need to make a mirror. Okay? That's the crucial ingredient. You can add a vector field with some mass term, so you're solving that Pro-K equation, or some massive tensor degree of freedom. Those are the equations you're solving on the background of a Kerr spacetime, of a Kerr black hole. Okay? If you do the calculation, there's a low frequency calculation that you can do that tells you the following. So all I'm doing is the stuff we've been doing here for the last days. Okay? You assume a time dependence that looks like that. I'm afraid of touching this. I want to change the. Well, let's try. Okay? So you assume this time dependence, you plug in the equations, you solve for the quasi-normal modes. It's exactly what you're doing. And you're going to find that the characteristic frequencies look like this for small mass mu. Mu is the mass parameter of your field. So the ringing frequency is roughly given by the mass. The field is oscillating with a frequency equal to the mass term. Okay? But then it either decays or grows, okay, with some power that depends on the mass of the black hole times the mass of your field, okay, to some large power. This power is here. It depends on the spin of your field. So S0 for scalars, 1 for vectors, 2 for tensors. Now, if you work this number out for a scalar field, and if you fine-tune this number, mu, you're going to get a time scale of order 1 second for a solar mass black hole. 1 second. Okay? It's unbelievable. You have this guy, 3 kilometer size, and 1 second alone is enough for it to take a small fluctuation of a scalar field and just grow, remove all the rotational energy and place it on the scalar field. Okay? It's an instability, it's removing rotational energy. Now, it's not a mirror. I mean, it's a massive field, and it's not a spherically symmetric fluctuation. You need to have some azimuthal dependence, right? So what you're doing to the black hole is not absolutely trivial, okay? Why? Well, because the mirror, what it does is actually to take your black hole, the mass term, removes rotational energy and places it on some state that's non-axisymmetric. That's your moon over here. That could be a moon of a scalar field, of a vector field, whatever you want. Okay? Time scales, 1 second, a few days, whatever. Now, you might argue, and you should argue, that this time scale of 1 second or days, first of all, it's nothing really a small time scale, but I was fine-tuning, oh, wait a minute. I was fine-tuning mu, okay? You need to fine-tune actually a lot. For a scalar field, this is a power 9. You need to fine-tune a lot, okay? But the universe is so nice to us that it gave us black holes across 10 orders of magnitude in mass. There's got to be some black hole for which mu is fine-tuned. That's the beauty of this, okay? Now, why is this interesting? This is interesting in the context of dark matter searches or new fundamental fields. First of all, I don't need to have any abundance of these fields. I can start with 0. It doesn't have to be a cosmological origin stuff. I start with 0. Some small quantum fluctuation occurs in the vicinity of a black hole. What this tells me is, well, okay, it's going to grow exponentially. There's no way around that. Okay? So 0, and then suddenly you puff up a cloud around the black hole that looks like this. Think about the moon. This configuration is co-rotating with the black hole. The final state, this stops, at least at this level of approximation, this stops when the cloud always has the same phase towards the black hole, right? So you have a state that's co-rotating with the black hole. So there's rotation involved. And this is super nice, okay? I'll tell you why. Now, but also, you don't need couplings to anything else. You just need gravity. I mean, you could have 0 couplings. It's a scalar field, doesn't see anything. It's still going to puff up a cloud, and it's still going to co-rotate with a black hole. And because it's a non-axially symmetric configuration, you do the calculation we did, wave equation, source term, you're going to find there's gravitational waves emitted. I don't think I sent that notebook, but I can. This system is emitting gravitational waves. This system is spinning the black hole down. Okay? The other thing is, it's most effective. I mean, I think you should think about the Compton wavelength here. And if you do that, you will realize that for a field of 10 to the minus 10 electron volt, then you're talking about Compton wavelength of the order of a couple of kilometers. So you see, the coupling mu is larger, is ideal, when the Compton wavelength of your field matches the size of the black hole, right? It locks onto the size of the black hole, and then this stuff goes berserk. But if you look at, I'm not an expert on this, but if you look at the constraints for fundamental fields, I think this is a massive vector, okay? You will realize, of course, that all the experiments we do need to have a threshold at some value of the coupling to the standard model fields. Okay, this is coupling versus mass. Otherwise, you don't see it, right? You're looking for it with our particles. But this process actually doesn't require any coupling at all. If you're able to detect gravitational waves or measure the black hole spin, you're done. You don't need anything. Okay? And again, to summarize, this is what you'd expect. A co-rotating configuration around the black hole. You might also have, of course, an accretion disk. It's spinning the black hole up. There's all sorts of dirtiness going around. But this is very robust. Okay?
Sorry, Peter, but what is the signature? I mean, what is the measurement that allows you to constrain this? Is the a spin of the black hole, or is the...
Yeah. There's a bunch of things that people are amazing. A bunch of things that people have come up with to measure this. But again, time scales, look at a 10 to the 6 solar mass black hole. If you fine-tune this coupling, you're talking about 100 seconds time scales. This is ridiculous. You know, the saltpeter time scale for accretion is 10 to 7 years. You have seconds. It's super effective. And it's a wonderful source of gravitational waves and of spin down. Here's a way that you can use to actually start looking for these fields. Okay? This is called the Reggie plane. You put on an axis the black hole angular momentum, and you put on another axis the black hole mass. Okay, and now you draw instability lines, instability windows, okay, on top of which, so above on this window over here, black holes are going to be unstable. The time scale that I showed should be smaller than roughly 10,000 years. Okay? That means, because 10 to the 7 is a typical time scale for a black hole to evolve, you shouldn't be seeing black holes, spinning black holes there. Because this mechanism would be so effective that would spin the black hole down and away from this window. Okay? This was done for a massive vector field. Okay? 10 to the minus 18 here, 10 to the minus 20, minus 19, 10 to the minus 20. So now the thing you need to do is, well, sprinkle that plane with observations. These are the red crosses. Yes. Okay? These are the red crosses. Now, there's errors in the red crosses, but if you trust those observations, so there's a lot of things that go into actually constraining the spin of a black hole, just to be clear on that, okay? But if you actually trust these observations, this guy over here, the black hole is called Farrell 9, okay? That guy alone should be excluding a massive vector field with a mass of roughly 10 to the minus 20 electron volt. That's 2 orders of magnitude, back then at least, better than what you'd get from particle detectors on Earth. You're doing particle physics with a supermassive guy, with a beast, with a gigantic astrophysical black hole. I know that the first question that people ask is, well, but man, wait a minute. You assume no couplings at all. It's a minimally coupled massive field. What about if the field is talking to the accretion disk or it's talking to the galaxy and so on? I don't trust that. Then you can't trust this, okay? But if you're dealing with a massive tensor, for example, couplings should be super, super small, and you would still get a bound of 10 to the minus 23 electron volt, which, by the way, now is on the particle data physics booklet from superradiance alone. Black holes now are doing particle physics. This is one way. So you measure the spin of a black hole. But because these systems are non-axisymmetric, they should be releasing copious amounts of gravitational waves, right? We have detectors. Let's go and measure them. Okay? This is one estimate. This now has a few years, I think 5 years or so. This is the number of expected events for LIGO, okay, if these clouds exist, and if you have a massive, in this case, scalar field with masses between 10 to minus 13 to 10 to minus 10 or so electron volt. We're always, if you're doing LIGO, guys, stellar mass black holes, just look back at the Compton wavelength, you're stuck to this region between 10 to minus 10, 10 to minus 13 electron volt. If you want to go lower in mass, you need gigantic black holes. You need LISA. Okay, but for LIGO, this is good enough. It's interesting enough. If the field exists, LIGO at design sensitivity should be seeing up to 10 to the 5 events a year, resolvable events. It's not backgrounds, it's single events that I see because the amplitude is so large. It's a monochromatic signal. Okay, I should be able to see this very, very clearly. LISA, the number of events is smaller just because we have a smaller amount of massive black holes. At least we think so. Okay? But still, in the range of 10 to the minus 17 electron volt, we're talking about 100 events or so per year. It's not bad. Okay? These are resolvable events. But now you think, well, but these guys, a black hole is born, evolves over cosmic times. The mass is changing, the spin is changing, it's accreting. At some point, it's going to lock onto that nice sweet spot of mu, Compton wavelength times size. It should be releasing bursts of radiation, right? So if you think about the entire universe, you should be having also large stochastic backgrounds of these waves. And you can actually use them to see how well you're going to do particle physics with this guy, okay? This is the stuff we've done at this point, which is current LIGO observations are now, because we know our sensitivity to stochastic backgrounds, what we're doing now is basically ruling out fields within a very small window of mass, 10 to the minus 12 to 10 to minus 12.5 electron volt. LISA, when it comes, 14 years from now, we'll be ruling out these guys over here, 10 to the minus 18, 10 to the minus 19 to 10 to the minus 15 or so electron volt. Just from the absence, just from not measuring gravitational waves. Of course, it could be that it does measure, and then you discovered something, okay? I'm being pessimistic here. But LISA can also do the two things, right? Because LISA can see stuff so well, it's going to be estimating very precisely the black hole spin, right? And it's going to see thousands of these guys. So here's one thing. So instead of looking for individual waves from these guys, here's what LISA could do, okay? You take all the black holes that you get, actually we just took 10 to the 3 or whatever, okay? And you assume they're evolving in the presence of a field that has 10 to the minus 16 electron volt. Okay? The abundance of this field is zero. You don't, again, this is important. You can start with zero field. The black hole will do the rest for you. Okay? Now, you evolve these black holes via accretion, in our case, and some of them are going to lock onto superradiance. They're going to spin down, lose mass to the field. So when LISA does the measurement, so we sprinkled this plane in an homogeneous way. This is spin versus mass. You wait 10 to the 7 years. LISA comes up, it flies, it measures the mass and spin of those black holes, and it's going to get this. A nice cutoff where black holes are not going to exist. Right? If this field exists in nature, LISA will find gaps in the Reggie plane. We'll not see stuff. They move away. They slow down because of superradiance. And you might wonder, oh, what is this? Well, these are different modes. This is the dipole mode. This is the quadrupole mode. This is the octupole mode, and so on. There's nice substructure in all of this.
Not always to assume that black holes initially have some spin.
Yeah. In fact, we expect it. In this case, we sprinkle them homogeneously between 0 and 1. It doesn't change a lot, even if you sprinkle them with a limit up to 0.7 or so. But of course, if you start assuming that all black holes start non-spinning, then you can't do this, right? So if there's something that we don't know of that for some reason gives rise to slowly spinning black holes when they're born, this will not work.
So far, the ones we've measured have a spin. Right?
They have a very low amount of spin. Who knows? Maybe it's some fundamental field that's spinning the black hole down. Now, I said there's different ways. This one summary of the situation until a couple of years ago. You either resolve events, so you take gravitational waves from resolvable events, okay, and you impose limits. For example, you look at Cygnus X1, you look at the spin down of this black hole, you look for a monochromatic signal, you don't find anything, then there you go, there's a constraint. You look for stochastic backgrounds, or you measure the spin very accurately, and then you know, well, okay, this is going to rule out some mass range. Or you look at the spin distribution of black holes in the universe, if you have plenty enough. By the way, I gave this talk a couple of years ago in Paris, where I showed the Reggie plane distribution. Should I go? I'm going there because this is interesting. And I think I have time. So here's the constraint, okay? I was telling people, look, this is fantastic. We're doing better than particle physicists. And somebody in the audience goes, well, you know, these errors, do you really trust them? I'm like, I don't know. I mean, this was published by somebody else. And the person goes, yes, one of the authors was me. So there you go. If you don't trust the errors, no, wait. So you can also actually use electromagnetic observations of light that passed through this stuff. For example, if you now assume there's couplings between light and the scalar, for example, if it's an axion, then you can also impose constraints on the coupling itself, not only on the amplitude, on the size of your cloud, but also on the coupling strength. And of course, you can use motion of stars close to these supermassive black holes because they are going to be sensitive to the mass here. If you take the S2 star in the galactic center and it's crossing one of these regions, of course the motion is sensitive to this, right? As I said, people think of everything. Perfect. How big can this become? Now, we saw with the calculation of the irreducible mass, we know how much energy we can extract from a black hole. If you start with a maximally spinning black hole, you can extract up to 29% of its mass and place it in a cloud. This is the absolute upper limit. Numerical simulations, either fully nonlinear or done in a perturbative regime, show that you can get up to 10%. That you get up to 10%. So values between 1% or 10% of the black hole mass are reasonable. It's not a far-fetched scenario. It's a lot of mass, no? I mean, just so that you have an idea, the gravity collaboration, which is looking at the S2 star in the galactic center, is constraining the total mass within this orbit to be 10 to the minus 3 of the black hole mass. Okay, that gives you.
What about the size?
The size depends. Good. The size scales like 1 over m mu squared. Okay, so it depends on the scalar field. So if you want coupling, so this is 1 over m mu times 1 over mu. Okay, so m mu you want it to be over the 1 if this is.
So, for example, you expect such a cloud at the center, at the supermassive black hole at the center of the Milky Way? You will have some.
Well, that's an unfair question. If there is a field with 10 to minus 18 electron volt, yes, it will be there. I mean, I don't think there's any other way. And now the size of this cloud is determined by this. We can calculate everything. We know everything about this. Yeah. So it should be there. Yeah. If the field exists, and I think anybody's going to have a hard time finding ways of getting rid of the cloud because black holes are spinning and it's really hard to give away the energy. These are the current constraints on, again, these are minimally coupled fields only. I'll go, if I have time, into what should be coming in the next few years. And you always find bounds that look like this, right? So you look at Cygnus X1, you don't see any waves from there. There you go. You're constraining the mass. It's a small range, okay? It doesn't look super exciting. But if you take all of these together, it gives you a wide range of constraints for these fields. I'm going to skip this slide. Now, this was done in vacuum, okay? But of course, most of the systems you find out there have companions. You might couple to the accretion disk and so on and so forth, okay? We started as a community to try to understand this. For example, if you take a cloud, a black hole with a cloud, and you place a satellite here, I don't know, a third guy over here, you can actually, it's a nice quantum mechanical calculation to see what the cloud is going to do. It's going to cause level transitions in this cloud that you can actually calculate. If it's close enough, it's actually going to disrupt the cloud, okay? This is one example of one numerical simulation that we did, if it plays. I don't think it plays. Nah, it doesn't play. Anyway, if you place a third body too close to this guy, you're just going to strip the cloud off the black hole, okay? You still spin the black hole down, it's just that you're not going to see a lot of gravitational wave emission. Very good. Now, this was the clean story. What happens in real life? What happens when I start adding plasma around spinning black holes? What happens if I couple the axion to the Maxwell sector? Okay? Now, the absolute honest answer is, I don't think we know. Okay? We need to start working on this. There's arguments that will tell you, well, some of these things should be actually quenched, right? Plasma is giving the photon an effective mass, and this can work both ways, right? Because photons in a plasma acquire a mass, you could think, oh, wait a minute, then the plasma alone can actually create one of these clouds. It's like a massive vector field. It extracts energy and then condenses around the black hole. It's nice, okay? However, of course, it's not a constant mass field, so you need to understand back reaction on this plasma distribution. This is not done, okay? You could also think that if you start coupling matter, this new fundamental degree of freedom to the standard model, there might be ways of escaping the instability. For example, look at this axion, okay? You have this guy, a mass term for your scalar field, and without any without any conversation with the photon, this guy would just grow. We saw it. Superradiant instability, the field psi grows and forms a cloud. But now, if you couple it to the vector, there might be a way out of this. Instead of growing the cloud, the guy could just dissipate under electromagnetic waves, right? We actually simulated this. So we took a spinning black hole, spinning at 0.9, okay? And you put there a scalar cloud. Here you go. This grew by superradiance. It's there emitting waves. It's very happy. It's growing on timescales which are large. It's all very fine. Then we turned on a non-zero coupling, but very small, a very small coupling, okay? And we threw a photon at the system, just to fluctuate a bit the system, to perturb the system. And this is what it happens. There's a small photon here. The system continues happily, growing via superradiance. Nothing occurs, okay? But now, we tuned K axion, the coupling, to be larger. And we did exactly the same. There you go. The vector goes. And you see, now things start to happen. Because the coupling is large, what you find is a parametric instability, and you just grow a huge electromagnetic field inside the cloud. What it does is steal energy away from your scalar field. It channels the energy to a burst of electromagnetic waves. This guy decreases, so it needs to wait and be grown by superradiance, so you need to wait a few more million years. This guy grows until the coupling becomes large again, then you find a burst. Okay? So there's a lot of possible phenomenology to understand, and I don't think this is nearly, even starting. Do I have 5 minutes? Okay. Now, all of this was done for real fields, okay? I throw in a wave, I see it's unstable. It's possible that you could have other scenarios, and those scenarios might actually give you a way to circumvent the no-hair results that we saw, okay? Now, if you think about why we have these no-hair properties, these uniqueness theorems, you will realize, first of all, the theorems are this. Any isolated, stationary, regular, so a smooth solution of the Einstein equation with a scalar field, then it has to be the Kerr family, if the boson is time independent. So if you try to place there a scalar field that's time independent, we did that for non-spinning black holes, you see that you can't do that. The reason is simple. The field will just be absorbed by the black hole. There's no way you can get around that. Okay? The second theorem is, if you have an isolated, stationary, smooth solution of the field equations with one real scalar field, it could be time dependent. But if it's real, then you don't have a solution. It has to be the Kerr solution. Okay? Why? It's not the horizon. It's because if the field is time dependent, okay, then that gives you a time dependent stress tensor that should be emitting gravitational waves. Okay? Now, we know how to circumvent both of these guys. Right? So instead of a real field, I can take a complex field in a way that the time dependence goes away when you build T mu. That will get rid of this guy. Okay? And if you give it some time dependence, that will add pressure on the horizon. In fact, if the horizon is spinning, superradiance might do the trick. Instead of absorbing, it can hold on the scalar. Okay? So there seems to be, at least in principle, ways of circumventing this. This was found by Carlos Herdeiro and Eugene Radu a few years ago. They found precisely this. They built a black hole solution which is spinning and has a cloud of a complex scalar field in its exterior. The cloud is co-rotating with the black hole. It has to, because we saw the final state has to be the cloud always with the same phase. Okay? Right? It's complex, so nothing is emitting gravitational waves. Everything is nice. It's an amazing new solution, I think, of the field equations. And if you wish to go into doublets and so on, it might occur. I mean, you might have this type of solutions. Well, let me finish with challenges when you start thinking about mechanisms to extract energy and away from black holes and to constrain new fundamental fields. First of all, I told you that we can do this for linearized tensor fields, vector fields, and scalar fields. But there's a slight difference between the tensor case and the rest, right? The rest is, we saw it here, assuming a curved background is a legitimate thing to do if you're talking about a scalar field or a vector field. It's not a proper assumption to take if you're dealing with a new tensor. Okay? So you need to justify very carefully, and I don't think it can be done, that you're using Kerr as a background if you're dealing with massive tensors. We looked at superradiance from isolated spinning black holes. It's quite possible, actually it's quite likely, that if you take a binary of non-spinning black holes, you also get superradiance there. But we don't know. The system is so complicated that just showing whether or not there's superradiance, it's a tough problem. So we don't know if this is going to generate superradiance and if this motion is going to grow a scalar cloud, for example. Okay, I think it's an important open problem because it gives you a new scale to turn on fields at even lower masses. Again, we don't know what's the effect of a plasma when we do back reaction effects, when we actually back react on the plasma distribution. I think this will take a few years. There are groups working on this, but it will take some time. And I think I'll stop there. Thank you.
So questions and comments?
Thanks very much for the nice talk. So if I understood correctly, as long as we are with a frequency below the mass, we pretty much have this mirror effect from the gravity.
That's right.
But in the standard model, in the symmetry broken phase, we have all kinds of fields with masses. Would those not automatically deplete all of the angular momentum of the black hole and therefore probably just hide any new particle fields?
No, because so most of those fields have huge masses. The mechanism is strongly suppressed. So it only acts really, I think you can think about it as only effective if the Compton wavelength matches the size of the black hole. All the others are really irrelevant. The timescale is orders of magnitude larger than the Hubble timescale for a pion, for example.
More questions?
With Event Horizon telescope-like observations, can we hope to put constraints on this kind of scenarios? Consider that we can, I don't know, have pictures of.
Yes. So yes, they are not super nice. The idea is to measure. That's a good question because it ties with the first lecture actually. The idea is to measure the size of the light ring. Okay, it's somewhere here, and that gives you an idea of the black hole mass if you're in vacuum. The Event Horizon telescope basically is aiming at measuring light ring sizes. Okay, so if you're in vacuum, that gives you an idea of the mass of the black hole. But then you can use the motion of stars around it, S2 for example, to actually measure the gravitational mass far away. They should match. If they don't, then there must be something between. That's giving you some constraints. They are not brilliant, but they are, if I remember, of the order of 10%. So the mass, if there is mass between the horizon and outside the light ring, it has to be smaller than 10% of the black hole mass. The constraint is not as brilliant as the gravity instrument of 10 to minus 3, but it's a start. Yeah.
Okay, thanks.
More questions?
I have a very naive question. So, will this effect also appear in, highly spinning pulsars or other objects which are strong?
So
potential
yes,
which
yeah.
spin very fast.
So we need to maybe. So this only occurs if the field sees the object.
Okay.
So if you find a way to couple, for example, if you do a minimally coupled scalar field on top of a pulsar, this will not happen. The guy doesn't see. You see, the ergo region does the trick in the black hole case,
Okay.
right? It's forcing the field to co-rotate. However, if you add some way that the field, for example, if you add some conductivity to the material, to the star material, then a vector field will couple to this. You will see this effect.
Okay.
In fact, you could use this to build a spinning sphere here that would give rise to.
Okay, we'll ask later. And the general question is, the other question I have is, typically when we do these indirect searches with astrophysics, typically we have a whole bunch of systematics, from measurements to things we don't know on the astrophysical system that may be degenerate with the signal we're looking for. So how does it look like for this type of bounds, no, of these superradiance? No?
Yeah.
What can go wrong that will
So,
prevent us or
right,
seclude
right,
the signal or
yeah.
the bound?
I
Because there
think,
is something
yeah, I think it's
complicated
yeah,
astrophysical that is
yeah.
happening.
From
no?
the
We don't know.
gravitational wave perspective, there's very little that can go wrong. We understand entirely the system is monochromatic signal. We haven't seen any
The gravitational wave signal.
in the gravitational wave signal. Yeah. So there's very, very little systematics that can go on. Gravitational waves interact very weakly. So I think we control, I wouldn't claim entirely the thing, but to a very, very good extent. If you're doing indirect constraints, like based on black hole spin, that's a different story. Because black hole spin, as I said, the errors that are published or claimed vary by orders of magnitude sometimes. And I think accretion might play a role there as well. So indirect constraints from observation of spins, I wouldn't vouch for it, no.
Okay, thanks. More questions? Okay, if not, let's thank Peter for his wonderful lectures. And let's welcome Olga to the stage.
Hear me? Yes, now. Okay. So, are you awake? Okay. Anyways, the other day, I think that I stopped here talking about Anita, these events that Anita detected, right? And that they were that they are really weird because they violate other constraints, for instance, from Pierre Observatory, right? We just saw this, right? So very good. Let's continue. Among other techniques to detect high energy and ultra high energy neutrinos, we have also air shower detectors of tau neutrinos, okay? Here, tau neutrinos. And this is all based again on this tau regeneration effect, okay? A mu neutrino produces a tau that decays and then produces another tau neutrino and so on and so forth. So for instance, we have this detector here which profits from this effect, okay? So we have a charge current interaction here of a tau neutrino, an ultra high energy tau neutrino that produces a tau, that produces a tau, and then it decays and reaches this, and produces an air shower that is detected by these tanks here, okay? So, for instance, Pierre Observatory is one of these uses this technique, right? And it's a large-scale array of surface water tanks to detect Cherenkov light from horizontal air showers induced by ultra-high energy neutrinos in the atmosphere. TAMBO is this array, right, that is planned also to detect these tau neutrinos, okay? So apart from that, we have also air shower radio detection with radio detection of Earth skimming new taus, and it's also a promising way due to the long attenuation lengths of radio waves in the air, okay? So it's the same than in ice radio detectors, and then one uses really, really huge arrays to instrument large areas, okay? So radio emission is generated in air showers initiated by tau decays via the geomagnetic effect, and then what happens is that you can detect these gigantic air showers by setting the radio detectors, right? So you can see here, for instance, Grand. I think that Francesca mentioned Grand, right? So you can see here again, there is a mountain here, a new tau comes, interacts, a very earth skimming new tau, produces a tau that produces an extensive air shower. Let me go back here. That produces here, that produces an extensive air shower, and this extensive air shower is detected via radio detectors, okay? So let me go back, this here, okay? So also we have air shower imaging, okay? This is another technique, right? So there are also air shower imaging instruments that they are in reality optimized for cosmic rays and gamma rays, but they can also be used for neutrinos, okay? So we recycle everything. So I have demonstrated that they can be used, and we have here some possible future scenarios as Poema, right? That, I mean, in which you are gonna detect anyways these huge, gigantic air showers via the Cherenkov fluorescence light, okay? So, I mean, many possibilities. They are quite cheap indeed, because, I mean, you just put their tanks or these things. Of course, you have to instrument very large areas, right? This is the most difficult part. But I mean, it's not like to build a super large linear collider, nor, you know, I mean, or something like that, nor to put, nor to send a satellite, right? That launching costs, right, as Euclid and such, are super expensive, right? So anyways, so here I show you the current and future experimental landscape, okay? So here I show you the flux of neutrinos in times E squared versus the neutrino energy, okay? So we have at low energies, we have the optical Cherenkov light detectors, right? That they are the best way to measure high energy neutrinos, okay, at low energies. And at high energies, we have air shower radio detection of Earth skimming new taus as the best pros, okay? So here we have this now, the limits are here now, right? From Anita or J, ice cube, sorry, again, ice cube, right? Measurements of ice cube of the high energy neutrino flux here, right? Here, let me see, here, okay? And then if I use this, you will get crazy with. So I mean, then in coming decades, we are expected to reach this sensitivity, okay? Future detectors. And I put you all the possibilities here, Tambo, Poema, Ice Cube Gen 2, okay? So we are really reaching limits, really interesting, of cosmogenic neutrinos, for instance, right? At some point we know they are gonna be there because we have observed the ultra high energy cosmic rays. So I mean, this will be also a major discovery, okay? Not only the high energy neutrinos, but the ultra high energy neutrinos, those which are in this area, okay? We have already detected high energy neutrinos, so now we have to detect ultra high energy neutrinos. Here I put you an example, okay? For instance, this is what IceCube has measured, okay? IceCube measurements right here. This is the limits, these are the limits here and here for from IceCube now for ultra high energy neutrinos, and those are these in blue here and here are expected from IceCube Gen 2. So we are really gaining a lot of sensitivity, okay? Like 2 orders of magnitude. So the isotropic is most likely an isotropic distribution, which points to an extragalactic origin, okay, as measured here. And then I show you here 2 possible models, one with a single power law another with a power law plus P gamma emission from a BL object, a kind of super huge cosmic accelerator that produces also neutrinos, okay? So both are provide a very good fit to the data. The statistics is not good enough to discard one of them, right? So realize that to find spectral features is very important because this will tell us about the maximum acceleration energies of cosmic rays. Okay. So now, can you hear me better now, right? So, okay. So here I show you the cascades and tracks as measured by IceCube. You know that there are two kinds of event topologies, right? Tracks and showers. And then also we can measure the spectral index, okay? You can see here the spectral index and also the events measured by IceCube, right? The spectral index meaning that. And you can see that the spectral index is roughly around 2 or so, okay? 2 point something, okay? And this is also very important to characterize the sources responsible for ultra-high energy cosmic rays and gamma rays, okay? Now, so, as we were talking the other day also, these measurements are super useful to constrain cross-sections, right, at ultra-high energies, right? So, I mean, where we don't have data from accelerators at Earth, okay, man-made accelerators, okay? So, let me show, I don't know why today is here, I mean, the other days was like, yes, now better? Okay, yes. So, I mean, realize that at energies of the order of GeV, right, neutrinos interact mainly via deep interacting scattering, or deep inelastic scattering, sorry, in which the neutrino exchanges, right, either a W or a C boson with a parton in a nucleon. A parton can be either a quark or a gluon, okay? So, the nice thing about high energy neutrinos is that they probe a small X region. I mean, X is the Bjorken variable, is the fraction of the total energy of the nucleon carried by the interacting parton, okay? And the small X region and the high Q square region. The Q square is the momentum that carried by the mediating boson, either the W here or the C boson, okay? And then this is really a very nice region because this is not available at colliders, at collider experiments. And you are going to see this much better here, right? You can see that this is the cross-section, the neutrino-nucleon cross-section, sorry again, the neutrino-nucleon cross-section here, right, versus the neutrino energy. And you can see here that these are measurements taken at man-made accelerators, while these are the measurements that performed by IceCube, okay? So this region is inaccessible to man-made experiments. So the only way to measure the cross-section in this region and in this one that we expect to measure it in the future is via these super powerful cosmic accelerators that give us these super ultra-high neutrino fluxes that we use to measure these cross-sections. By the way, here I show you also the different errors, the theoretical errors, right? So I mean, it's very important because it can change by one order of magnitude. And this is very important because cross-sections are crucial to test standard model and beyond the standard model physics, okay? For instance, scenarios with extra dimensions or exotic things, new particles, right, are super useful, yeah. The events that you measure. Yeah, the flux and the flavor composition also is very important. Yeah. But mainly the flux. Yeah. This is important because, I mean...
But you need to model the astrophysics.
Exactly. You have to model the flux also, yeah. So many of these limits, right, you see here, right, that they assume, you see, right, they assume a given model. Of course, not this. These are the well, when you look to the predictions, sorry. When you look to the predictions, they assume a given model. When you are dealing with data, of course, you have the data and then, yeah, but I mean, yeah. You have, the disaddegeneracy, of course, but still, I mean, it's the only way to tackle this, to measure these energies, okay? Another possibility that we can do is neutrino decay, okay? Neutrinos can decay, right? Yes, over cosmological times, right? So, I mean, here I put you the limits on tau over m, right? The decay here, right? The lifetime of the neutrino over the mass, and you can see that, of course, CMB is the most powerful measurement, provides the most powerful bound, but also the diffuse supernova neutrinos, neutrinos from the supernova in 1987A, and also ice cube, right? You see that also ultra high energy neutrinos, since they have traveled over very, very long distances, they provide also a very nice test of neutrino lifetimes, okay? And the way it enters is in the probability, in the oscillation probabilities, is instead of having these weighting factors, we have this exponential here, okay? Which depends on the lifetime. Dark matter, we have seen this in both Tracy Sladger's lectures and Francesca Callore's lectures. As you know, I mean, the WIMP is the most attractive, let's say, particle candidate for dark matter, right? So, I mean, the WIMP scenario implies somehow that dark matter today, there could be ongoing annihilation of dark matter particles into neutrinos, for instance. In principle, the dark matter particles annihilate or decays into any possible standard model particle. And this is going to produce for sure neutrinos and gamma rays as final products, okay? So, I mean, you can clearly see here that Antares provides very, very good limits, right? Because it has a very, very good location. Right? It has an optical location. Antares is an array located in the Mediterranean Sea, okay? So it has an optimal location to observe the galactic center. And then afterwards, we have limits on the dark matter annihilating cross-section here, right? From ice cube also, right? And at high energies from Oye, okay? Here. So I mean, Oye, here, okay? Very good. So also, we can test fundamental symmetries with neutrinos, okay? Very good. I mean, there are people here working, for instance, in Lorentz invariance violation or in CPT violation. And then what happens is that from this expectation that we had right here for the neutrino flavors in the triangle that I showed you the other day of the fraction of nu e, nu mu, and nu tau, right? And the standard probabilities, we will have something like this. So, I mean, you know, I mean, this seems that the parchis, I don't know if you have played to this, right? I mean, so what is the correct model? Okay, it's quite difficult because we have a contribution from a Lorentz invariant, for instance, part to the total Hamiltonian, the standard 1 plus this, and then the probabilities cannot be longer unitary or something like that. You have deviations from the standard picture, from this standard point that we are expecting, and then how well do we measure this depends on how big are these fluxes, right? Depends on our statistics. Okay, so just final remarks, what we can do with neutrinos, because I'm going to move now to something that I think that you will find more interesting, maybe or not. So, but you are going to listen to me anyway. So, so here I show you, right? What can we do with neutrinos, right? Everything. So, I mean, we can do Majorana versus Dirac, CP violation, flavor mixing, test the cosmic backgrounds, neutrino decay, depending on what kind of sort of neutrino you are looking at, of course. Supernovae, solar neutrinos, geoneutrinos, reactor, long baseline, atmospheric, ultra high energy. Here we have the GCK cutoff, right? Dark matter, sterile neutrinos, in all this, right? We heard about the sterile neutrinos, right? The sterile neutrino, this claim that there is this sterile neutrino spectral line that we were talking the other day, or with Francesca, right? So, I mean, there are plenty of possibilities. So, neutrinos are the future, okay? And, okay, so let me move now to a totally different thing, that is the Hubble constant tension, because neutrinos can also fix the Hubble constant tension, as you will see. They can do everything. Anyways, so, you know, right, that there is a tension related to the Hubble constant. And this is a disagreement between 4 and 6 sigma, depends depends what you look at, right? But in general, it's between 4 and 6 sigma, depending on the data set. And rather than diluting, here I put you this plot from Wendy Freeman, rather than diluting when measurements have become more powerful, and of course, the errors have decreased, it has increased in significance with time, okay? Here you can see the Hubble constant H0 as measured by Cepheids, CMB, and the tip of the red giant branch, right, that basically uses a different type of stars or objects to measure distances, okay, just this, right? And you can see, right, that we have versus the year of publication. And we have here the CFAs, we have here the CMB, and in the middle, of course, in the middle, we have the other one, right? So who is right? Who knows, no? Okay, so let's see what happens here, right? I mean, maybe this goes up and this goes that way, right? So, I mean, the value measured by the Planck collaboration by early probes, right, is 67, sorry, plus minus 0.6 roughly, and the value measured by late time probes, for instance, by CFAs, calibration by CFAs, is 73 plus minus 1. So this is a phi sigma discrepancy, okay? There are some cosmologists that believe that such a tension is not there. There are other ones that believe that this is a big issue. And what is it? Okay, I don't know. I mean, so early measurements, okay? So they are a prediction within a model, okay? So early measurements do not measure directly H0. They have to assume a model. And I'm not saying that they are wrong, okay? But they have to assume a model, okay? Okay, I'm not Alan Rees, okay? Anyways, so they are a prediction with, even though he's a collaborator of mine, and I really admire, I really like him a lot, but I mean, I have to say things as they are. So, I mean, these early measurements tend to increase from the Planck 2018 TT baseline with inclusion of data. So they move, here I show you, right, in this whisker plot, up in the early indirect measurements, down the late measurements. Here, the measurement of 73 plus minus 1. Here, the measurement of 67 plus minus 0.6, right? And here where they lie. So you can see clearly that early measurements lie here, while late measurements lie here. Okay, we will see those. Those are kind of huge error bars, but okay. So, I mean, late measurements, right, are the best established and unique empirical methods to measure H0, okay? They use the distance ladder, right, as a way to calibrate luminosities of stars that after can be seen at a larger distances, okay? So you measure some here and then you go there, it's like a ladder, okay? So we have, of course, the Schurz theme, and that uses CFAs or supernovae 1A to calibrate distances, okay, as standard candles, okay, because we know the luminosity, okay? So there have been many analyses of this data, and all of them agree on this high value of H0, right? And you can see this here, right? All these analyses with CFAs give a large value of H0, right? One can use other type of objects to calibrate distances. For instance, the tip of the red giant branch, which is something in the middle, mega major galaxies, right here, the surface brightness fluctuations method as a distance indicator, also by measuring the fluctuations in the brightness of a galaxies depending on the number of stars within them, okay? And also one can use the Tully-Fisher relation, which uses an empirical relation between luminosity and rotational velocities, right? So, and you can see that all of them, right, all of them are here, okay? All of them, right? So, I mean, maybe the tip of the red giant branch is somewhere in the middle, right? But all of them basically lie there, okay? So, gastrophysics model-dependent limits, okay? So we have time delays in strong length quasars. They are more model-dependent because they have to assume something about the length in mass distribution, right? So, I mean, they have already a model dependence there, okay? They are not pure empirical methods that don't use any input, okay? And then we have, of course, standard sirens, okay, here, right? Also here, right, which are gravitational wave related. So, oops, sorry. Let me go back. Here. Okay. So systematics could be systematics. I mean, the problem is that one systematics won't fit the issue. One needs a lot of several sources of systematics, plenty of them, and in each of the probes. For instance, there could be calibration issues in supernovae. We could have also different populations between local and the Hubble flow supernovae 1A, okay? In the populations of the supernovae 1A, okay? We could be living in a void, but I mean, the required underdensities would be totally unrealistic, you know? I mean, so no way. In the case of strong length quasars, one can think about the length profiles, but I mean, it's not only strong length quasars, those that are giving us this discrepancy, right? Are plenty of probes. This is the problem, right? Okay, is the cosmological principle wrong? Okay, I mean, this is another possibility, right? I mean, this is like many years ago they were discussing if it was 50 or 100, the Hubble constant. But in that case, the discrepancy was among tests that were dealing with the same observations, okay? For instance, imagine that shoes, one analysis of shoes sees 68 and another one 73. This could be something systematics related, but here we have many different probes that point to isolated values, okay. How do we measure the Hubble parameter from the CMB? So, from measurements of the matter and baryon densities within a model, right? One computes RS, okay, the sound horizon at the last scattering surface, and also the last scattering redshift, okay? Then, from the measured position of the CMB peaks, one can extract the comoving angular distance, okay? Okay, one extracts dA. One computes this within a model. This, you measure it, and then you extract this. And once we have the angular diameter distance, we infer the value of the Hubble constant, okay? So the question here is, could the last scattering surface be closer? Or could the CMB spots be smaller in order to agree with late measurements? So the recipes, this is what we do, no? So I mean, we have to fix the problem, right? So we have to play with this quantity. We can play either with dA or either with RS. So one can find early universe solutions. Early universe solutions change both RS and dA at recombination to have a higher value of H0. This is the recipe for early universe solutions, okay? Late universe solutions, what they do is that they change dA at redshift after recombination to have a lower H0. So, I mean, in this sense, early universe solutions have more freedom, right? For instance, you add how can you change RS, for instance, right? So you include a dark matter baryon interaction. So you change RS. Of course, you change the speed of sound, right? So, I mean, there are many ways in you can change RS. Also playing, for instance, with an effective, right? You can change RS, right? Adding more relativistic stuff, you can change RS. Playing with actions. So, I mean, you can do whatever you want, basically, right? I mean, well, not whatever you want, but there are plenty of models that can change RS, okay? So, late universe solutions are more delicate because you can only just play with dA. And then the thing is that you should be careful because you are supposed always to leave unchanged the angular location of the acoustic peaks, the angular location of the matter radiation equality area, and also the diffusion scale, okay? So you have freedom, but not that much. There are some rules. But here the neutrino comes, okay? So what happens? Let's start playing with the neutrinos to see if we can do something with the Hubble constant tension, okay? So first of all, the obvious thing, N effective. I mean, so N effective, yeah, of course. I mean, if you increase N effective, right, you will have a larger expansion rate in the early universe, so you will have a shorter RS. And the recombination needs to be smaller, and H0 is inversely, you remember, right, that dA, right, is proportional to 1 over H0. So if dA is smaller, H0 should be larger. Very good. So now we are in agreement with this late time measurements. But what happens here? I can show you this, right? Here, this is a plot from the Planck collaboration, where you can see that as I increase an effective, H0 increases. This is the measurement by Ries et al., okay? And this is the value of an effective that departs from 3, okay? But we have also the sigma tension. So I fix this, but I make this worse. The sigma tension is a tension between CMB and weak lensing measurements of the clustering parameter sigma 8. So it fixes, here you can see this discrepancy, right? Here Planck data, and here, for instance, DS measurements of sigma 8, right? So I mean, and what happens is that you fix one, you try to fix one tension, but you increase the other one. So I mean, no way, no good, and it's no good. And moreover, the tension is not really resolved, because changing N effective, there is still a 3.4 sigma tension, which is still there, okay? So N effective is not a way of doing things, okay? Okay, but neutrinos can interact, okay? May have unexpected interactions, okay? Neutrinos can give us surprises. They have given us plenty of surprises, and can have unexpected interactions, right? So keep this in mind. Free streaming, oops, no, this, okay? I mean this, here. Free streaming neutrinos travel supersonically. Again, yeah, I mean, okay, I won't use the pointer, and that's it. Travel supersonically through the photon baryon fluid in the early universe, okay? So they induce a phase shift in the CMB power spectrum given by this formula, okay? And what happens is that the CMB moves, right, towards larger scales, okay? That is smaller multiples, right, that way, right? Leading to a physical size of the photon south horizon and lattice scattering that is slightly larger, okay? This is what free streaming neutrinos do. So if we add an interaction, what happens is that they will shift the power spectrum towards smaller scales, okay? And also they boost their amplitude. And then they reduce, again, the physical size of the photon sound horizon, again, a smaller value of dA, and then a larger value of H0, okay? You see, the game, right? We have to leave theta unchanged. So if we change RS, we need to change dA, and then in the right way, of course, right? So, and then you will get this higher value of H0. And here I show you the effect of interacting neutrinos in the CMB. You can clearly see here that for this model, right, that has a G effective of 10 to the minus 2 MeV, right, minus 2, sorry again, here, you can see that there is an enhancement of the CMB, right, and also a shift towards, a small shift toward larger multiples, okay? So, in principle, if neutrinos are not free streaming, they interact, right, they could fix this H0 issue. So, here I show you some example. If the mediator is heavy, the picture is similar to the usual neutrino decoupling, but I mean the only difference is that neutrinos keep scattering with each other after weak decoupling. Okay, so you have a mediator there, and the effective coupling constant can be much larger than G Fermi, right? So I mean, neutrinos experience again scattering after the coupling, and increasing G effective. I mean, what we do is that we delay the neutrino free streaming period, okay? Interestingly, these authors, Sir Racine and Olivier Doré and others, found a mild evidence here for an interacting mode. Here you can see, right, this is the logarithm of the effective coupling constant of this putative new interaction, right? And you can see here, right, that they found this evidence, here with a value of G effective equal to roughly, I think that was 10 to the 9 times G Fermi, okay? This G effective, okay? And they found this evidence here. And indeed, in this case, you can see here the value of H0. If here we have in the plane of H0 sigma 8, you can see here that in this interactive mode, H0 can be much larger. You can see it, right? You see, right, that you enlarge this lambda CDM, H0 is here, can reach even values of 76 or so. However, that's not, I mean, in reality, things are not so good because, I mean, a reanalysis of this, including also high multiple polarization data, even if they cannot discard for sure this strongly interacting mode, is this SI new strongly interacting mode, they really, it's no longer favor, okay, when one adds polarization, CMB polarization data in the analysis, okay? So, not very good perspective for this model, And here I show you the current status on this, right? That is not really a good thing. One thing that seems nice, right, and really seems to solve the issue, are models with a majoron. Okay, the majoron is a pseudo-Goldstone boson, okay, associated to lepton number violation. Okay, so I mean you can have models with an EV mass majoron, right, interacting with neutrinos before recombination, and then you will relax a bit the Hubble tension. You can see this here, right, in here, let me put this, the tension is notably reduced, you see, right, that instead of being in this column, we are moving that way. And you can see here the lambda CDM model, and when I add this majoron model here, you can see that shifts to larger values of H0. Okay, here's the 1D probability posterior distribution versus H0, and you can see that if I add this majoron model with this coupling, right, it can solve the Hubble constant tension if I add this extra interaction. With the nice thing that majorons are very nice because I mean they can be embedded in neutrino mass models, for instance, of CISO and such. Okay, so majorons, I like them. I also like axions because they solve many problems. I mean, if one introduces a particle and solves just one problem, this is not good. But I mean, if one introduces something that fixes several problems, this is good. SUSY, for instance, was very nice, supersymmetry, because apart of fixing the issue with the standard model hierarchy stuff, also was a candidate for that matter. But it's now we are now cornering SUSY really in a really small area, right? Allowed region. But okay, I mean, also actions are very nice because they can explain the strong CP problem, and also they serve as a dark matter particle. Okay. Also, we can have interacting neutrinos, but in the sterile regime. Okay. Instead of having interacting neutrinos, the active ones, sterile neutrinos can also, if they are there, can also have interactions, and indeed are expected to have exotic interactions because they are not, in principle, standard model particles. So, I mean, and the nice thing about this model, as I told you before, is that it solves another issue. And the issue it solves is that sterile neutrinos also provide a very nice explanation of short baseline neutrino oscillation anomalies, okay? So there are some anomalies in neutrino oscillation experiments when one goes to very short distances, not of kilometers, distances of 100 meters or so, in which it seems that there should be another neutrino because they point to a very different mass scale, okay? Mass gap. So, I mean, these models that include interactions of these sterile neutrinos are very good. Why? Because cosmology in general does not like sterile neutrinos, because I mean we are putting bounds on the number of extra species and on the mass, and we are seeing that indeed, I mean, the values preferred by oscillation experiments don't match with cosmology. But if I include this interaction, what it will do, if I add this interaction, what it will do is that it induces an effective potential in the early universe that blocks the thermalization of the sterile neutrino. So, I mean, the sterile neutrino won't count as an active neutrino, will count as less than an active neutrino. And then I can reconcile cosmology and oscillation experiments, okay? So you can see here how this H0 value increases, okay, when I add this with respect to the lambda CDM model when I add this interaction, okay? So these models are also very nice. So in the ranking here, I show you now the ranking, excellent models. We have a lot of not only neutrinos. We have here dark energy in extended parameter spaces, phenomenological emergent dark energy, elaborative vacuum metamorphosis, generalized Chaplin. We have, among all these possibilities, we have also sterile neutrino interactions, okay? These are excellent in the sense that they solve the Hubble constant tension, and they reduce it to a fluctuation. I mean, it's less than 1 sigma. So if the tension remains at 2 sigma, we have good models, and then if it remains at 3 sigma, we call them promising, but to me, they are not promising, okay? So, I mean, if the tension is reduced just to, I mean, from 5 sigma to 3 sigma, this is not really to solve a problem, you know, I mean, so. But we have these neutrino-dark matter interactions. So, I mean, in principle, they are another way, but, I mean, the best way would be with sterile neutrinos, okay? So, I would like to thank you for your collaboration. I would like to thank the organizers. I'm done. I mean, today you are tired, I think, right? So, I would like really to thank the organizers, to Carlos and Jorge, because they have done a great job. I mean, they have put together a lot of young people from many, many different nationalities, many places in the world, and you are the future of physics, right? Because, I mean, I want to finish this also thanking my collaborators. You look at them, men, women of different ages, different seniorities, different nationalities, and all of them equally important, of course, and highly relevant to continue working. So, I mean, these schools are very, very important because you are going to know each other, and probably many of you will be strong, I mean, very strong collaborators in the future, you know? That's why you have to make huge connections until very late at night, okay? So, anyways. So thank you in many languages, and just let me finish with this, that I didn't have time to translate it, but what I want to insist is that science needs to be diverse, and to make science diverse, people that make science needs to be diverse, okay? So this sentence is from Belle Burnell. I don't know if all of you know the story of Belle Burnell. She discovered pulsars, and she didn't get the Nobel Prize. It was her thesis advisor, the one who got it. And what she says in this sentence is that science has been done, or physics and science, for years and years and years, have been by white men, okay? So, I mean, this is not good because, I mean, other minorities, as women or other sort of minorities, can look to problems with from a different viewpoint and provide solutions that these white men cannot see, right? I mean, we know this. I mean, there are fantastic Indian mathematicians. I mean, Chandrasekhar, right? I mean, he did a calculation in a boat with 25 years. I mean, you know, I mean, so... And this is what is nice from this school, that you are very, very diverse, and you are making connections for your brilliant future, whatever it is. I hope that all of you remain in physics and in academics and in research, but if not, I really wish you the very best, and thank you very much.
Thank you, Olga. Okay, so this was the last formal lecture of the school. So do we have any questions for Olga or comments? No? Okay.
They want to sleep. They want a siesta.
I can ask a very quick one. When you talked about the sterile neutrino solution, is it, and you were mentioning it can solve both problems, do you actually mean with the same parameter space that solve the double tension, you can also solve the baseline experiments, or just the model of sterile neutrinos solve both in principle? I mean, yeah, you will have to play with the mixing angle and such, but in principle, it could reconcile this tension. Yeah. In the same parameter space. I think they have a common analysis, including also short baseline data, but we can take a look to this, or we can write a paper on this if they didn't do that, right? I mean, so yeah. I mean, normally they combine this in this analysis. They combine you compute the abundance of the stellar neutrino in the universe, and with this, and for this mixing angle, you fit short baseline data. Yeah.
Any more questions? Actually, I have one while I go there. Besides neutrino oscillation experiments, is there any other way we can test these self-interactions, either in the lab or with some astrophysical observation like
Yeah, of
supernovas.
course. I mean, yeah, sure. In supernovae, for instance, in dense environments of neutrinos, right? Supernovae neutrinos have established. They put robust bounds on neutrino self-interactions, of course, because I mean, you have there solar neutrinos also. Anytime you have a dense neutrino gas, you can put bounds. Yeah. Yes, I mean, yes. With the future supernova observations, you could put really strong bounds. I mean, with supernova 1987A that were like 15 or I don't know, I mean, less than, we put bounds to so many things. So, I mean, imagine that now there is a supernova explosion, far enough, okay? And then illuminates our super Kamiokande that now is full of gadolinium. Can you imagine? I mean, we could put bounds to so many nice physics. I mean, yeah. Gravitational lensing of neutrinos from a supernovae. Neutrinos from a supernovae can get lens, right? I mean, a focusing effect if you want, right? So, and since neutrinos are not dangerous, we don't care. So, I mean, well, I mean, there are theories that the extinction of the dinosaurs was caused by a lensed supernova explosion. Yeah. So,
Hi, Olga.
anyways.
So apologies if I missed something, but from the contours that you saw for solving the tensions, I had the feeling that what these neutrinos solving mechanism actually what they were making was actually make the errors bigger, and then you didn't have like that problem anymore. But they were not shifting really that like the marginal.
Yeah, I mean,
statistics.
sometimes they play with that. You mean here, for instance?
Yeah.
Well, I mean, here the width is not that large.
Yeah, that's true.
Realize that here, this is the lambda CDM plus an effective, this is the majoron plus an effective. I mean, the width is the same, right?
Mm-hmm.
It's shifted a bit, right? But the problem is that this model also makes the sigmoid tension worse, while the majoron one no. But yes, I do completely agree. Many times, what happens is that you increase the error bars and then you fix the issue. I mean, for instance, when you assume an equation of a state of the dark energy that is negative, a phantom thing, you can also solve this, but it's because H0 gets very, very large error bars. There is a huge degeneracy. Yeah, sometimes it's true that they play with that. Yeah, enlarging these error bars, right? Here, right? So, I mean, yeah.
Thank you.
Thank you.
Okay.
Are these error bars coming from experimental data or are these theoretical uncertainties? Because like you don't know the parameters of your Majorana, so you introduce more theoretical uncertainty. Is it?
I mean, yeah, normally it's because you do the analysis and new degeneracy is open, right?
Mm-hmm.
You know what I mean? So I mean, it's just the error you get when you infer something from a fit to data, right? I mean, you have a freedom in the parameter space, right?
Mm-hmm.
Is what your question?
Yeah. So basically, it doesn't reconcile the two measurements. It just says that okay, Hubble can be somewhere within this error band, but once you fix it, you still have to
Account for this error bar. Yes.
No, like I mean, the true Hubble parameter should be somewhere inside that peak,
Yeah.
but it still is not in the agreement with the left and right measurements. So like we need to distinguish theoretical uncertainties and error bars coming from measurements.
No, those error bars are from measurements, of course. Yeah. They are not theoretical uncertainties. No.
Okay.
No. Yeah. When I saw this, okay.
More questions? If not, let's thank Olga again
Thank
for
you.
her wonderful lectures.
Thank you. And still we have 2 lectures, right?
No, one.
We have to talk this afternoon, no? 2 talks this
Don't
afternoon.
scare me, Olga. It's one lecture,
Who is
and,
missing?
and a public talk.
Yeah, and the public talk, yeah.
Okay,
Thank you very much. Thank you. And moreover, in this super nice place, I mean, that is Canary Islands, you know, I mean, this is, you know, amazing. Yes. I mean, I'm gonna move here when I will